I'll give a very, very quick introduction, and I also say that we're very thankful to have Professor Assa here with us. I met him, I guess, many years ago when I was giving a talk in Montreal. I think I was not a PG student anymore, but since then, lots of things changed. Hirbod jumped from university to university. He was at Liverpool at some point, right, at UFAM, and then Kent Business School, and now you were at the University of Essex.
Yes.
And every single school here was leading leading a unit or something. So it was a very exciting career, I guess, right?
Yes.
All yours now. Thank you very much for coming.
Thank you very much for the invitation. So let me see how I can just shoot people. Okay, thank you very much, Ed, for invitation. Actually, it was on the short notice, and I very much appreciate it inviting me because a month ago I decided to travel to Toronto for an event in Business Institute, and then it also invited me. So yeah, my appreciation for this invitation. That is the first thing, and the second thing is that this is part of the larger project that I started since COVID. Which is part of my endeavor to understand systematic risk, right? So it seems we are still challenging to understanding what is systematic risk, right? That doesn't mean that there is no paper in the literature that studies systematic risk, but I want to say that there is no unified framework to some extent to understand the extent to which that has an impact on our life. So for that reason, first I'm going to motivate. This is the same motivation that I presented at Business Institute, because I'm saying these works are belonging to the same project, but there I presented mostly the mathematical side, the principles that we expect to see when we are dealing with systematic risk. But here I'm just like an economist trying to give a model, to introduce a model that can give a meaning and bring everything from the sky to the ground, right? So that is, then we can start doing some sort of calibration, modeling, assessment, and so on, right? So let me start with motivation. Actually, I'm very much interested in problems associated with the macro event risk, right? That means with large scale and significant impact. For example, like COVID, and not exactly COVID, because COVID has many aspects. Mainly, I'm interested in the economic impact, right? For example, when we have a shutdown, economic shutdown, what would be the impact on the whole economy, right? I can give you two examples to explain more what I mean by that. Most of them are from UK, so let me just read it from the slides. According to the UK Government Office for National Statistics, during COVID, for several months, 27% of the workforce have been on furlough, right? So, and furlough means that you are on unpaid leave. You are not fired, you are on unpaid leave, and government is paying for you. And you can imagine more than 1/4 of the workforce in UK was paid by UK government. The first stage was for 6 months, then they extended that. So you can see actually how much money was spent, actually government was spending on this. So this is very, very large impact. The second example is again from UK during COVID. During COVID, UK government has decided to support businesses through trade credit insurances or TCI guarantee. As of April 2020, there was over £171 billion loss for the supply chain. And you know, trade credit insurances are very important insurances, usually are for business interruption, right? But they are not designed for this scale. That means when the whole supply chain, for example, is impacted by something. For example, in UK, nobody would go to restaurant, nobody would go to cafes. So that's why you had a lot of drop in the demand, right? So, and this was a huge impact, right? At that time, Rishi Sunak, who is now the prime minister, was the chancellor, and chancellor means finance minister in UK, and he decided to back up this actually TCIs through a reinsurance contract. But the question for me was that all these look like very much risk management schemes, right? So they are managing the risk at the scale of the whole economy, right? But why risk management was not in the center of discussions, right? Because I'm doing risk management, I was considering that these problems needed to be studied by us, right? Whereas usually economists are addressing these things, right? So especially because I'm doing a lot of insurance, for me, the question was why insurance is not part of the solution. And the short answer is that because they are systematic, and unfortunately, or because insurance has limited scope, the answer is that they are on systematic risk, and insurance is not designed for systematic risk, right? But then you can ask another question: what about any other risk management solution, not only insurances? So this is a very legitimate question. The answer can be either there is no, and if there is nothing that can help, why? And if there is, what those products should look like, right? And is it that we have to change the paradigm, or is it like we have to work on the risk management paradigms that we know and try to do something that that works, right? Okay, I studied this for now 3 years. Now it is becoming very clear to me that the existing paradigms cannot help. So that's why we need to change the paradigm. Particularly, we have to move from ex-ante policies to ex-post policies. I'm trying to popularize the idea. Ex-ante is like insurance. First, you pay the premium, and then you expect when the damage occurs, you'll be compensated, right? Whereas ex-post means first you are compensated for the damage, and then over time you're going to collect the premium. And this is really what is happening, because at the time of COVID, there were actually governments all over the globe started to inject money into the economy because we needed money. So that is why we would say this was the compensation coming first. But now we are just paying back the premium, and the premium is through running taxes, running inflation and paying high taxes. And now we can see in Canada, in UK, in US, we have high inflation, and that is because to some extent we are running an ex-post policy, right? We are just paying back the money that we spent during the COVID, right? So all these things now need modeling, right? Okay. I developed a mathematical perspective. I presented 3 days ago or 2 days ago. But the continuation is, okay, if you have a good mathematics now, what are you going to do on the ground, right? So that is why I need to do the modeling, right? And also want to say, what is the difference between systemic and systematic research? Because usually people interchangeably use them. For that, I have this diagram. This is presented to some extent in a book chapter I co-authored with Tim Boonen, my colleague. And we said to understand that, we have to understand what are the risk layers, right? And we presented this diagram, not in the book chapter, but we explained this diagram step by step, that the risk environment can be partitioned to different parts, right? First of all, we have retail, and that is because we have retail market. And this partitioning is, by the way, according to the markets, right? It is not arbitrary, right? We have observed what are the markets and then decided to do this partitioning. First, we have retail market and retail risk like car insurances, health insurances, and so on. Then we have corporate level. Corporate level means, like, for example, reinsurance contracts, which is at the level of corporation. like corporate bonds, all these are designed for risk management at corporate level. Then we have catastrophic level, which we know because of the catastrophic events. It needs a little bit of more elaboration because we have to come up with some sort of, for example, contracts and then design some ILS, insurance-linked securities, and transfer the risk to financial markets. Then we have systemic, which is due to system failure, and it's going to be very large. I have to say that up to catastrophe, we have markets for them, but for systemic, we still don't have any market for that. There have been discussions by Merton in the past and Bob Schiller as well, but to a good extent, this hasn't happened in a full stack, right? And then we have macro, right? Macro is very much what we have seen in COVID, right? And there is no market for that because everybody is in loss and nobody is ready to buy anybody else's risk, right? So that's why not going to be any market. We cannot expect that. But there is one solution. You can create a market with the people that don't exist. And the people that don't exist are the people of future, the next generation. And you sell the risk to them, right? And they don't have any choice but to buy it, right? And that is what we do. Running inflation means that we already have sold the risk to the next generation, right? This is the market which is moving towards time. This is not a market that happens at the same time. And then we have X-risk. X-risk, I didn't mention in the book chapter. It's not the subject that I'm going to study here, but if you're interested, this is existential risk. Nowadays, it's becoming really important because of AI. If you want just to study that, there is an institute at Cambridge University and also recently at Stanford doing research on this topic, but it is not a subject that I'm going to focus, right? So now, very long introduction. Let me start a little bit of math first. Okay, so now after this, I have enough motivation to understand the models and the tools that I can use in order to understand systematic risk, right? The model that I'm going to propose, I'm going to call it factor models, right? And essentially, this is because this is some sort of extension of the factor models that we know from past, but it's more sophisticated, right? So a factor risk management has been developed in scattered areas of research in the literature of finance and insurance. This is not, I would say, very new, but there has been a need to organize all these thoughts in one unifying framework, right? So our view is to make sure that the following perspectives are already met. Factors are the main systematic risk drivers. This is one thing that we want really to have in our models, and they are present in both modeling and also risk management, right? So having these two in mind then help you to understand what I'm going to do. So if you look at the literature, you understand that mainly we have two types of risks in a pool, right? Or let's say in a large portfolio. Either we consider they are independent. For independent, all risks are idiosyncratic. They are not systematic. And the way that we usually manage the risk is by diversification or pooling, right? And the other one is where we assume that all risks are co-monotone, like in risk sharing, when we are dealing, for example, with reinsurances and so on, right? Here, all risks are systematic because they co-move, right? Systematically co-move. And the solution that is in the literature is not diversification, but risk sharing, right? These are the two ends of the spectrum of risk management, right? So we are interested to create something in between that is not fully independent, all idiosyncratic, not fully co-monotone, which is all systematic. How we can sit in between, right? This is the okay, we propose factor models that is neither independent nor co-monotonic. So that is why we need materials. What are the materials? We need idiosyncratic risk material. We need systematic risk material. In addition to that, because we are trying to come up with a large portfolio of different risks, we also want to have heterogeneity, right? Heterogeneity is really important. It is not taken care of very much in the literature, and that means that the individuals are to some extent different, right? I also want to have this in my model in addition to having idiosyncratic and systematic risk, right? So I'm going to show how I can manage to have all of them in a model, and then I'm going to establish a law of large number for that, which is not really trivial. We need assumptions, but assumptions are making sense. And also I have a central limit theorem for that, which is going to help us to do the risk management at a large scale. And then we have very good results out of that. For example, we're going to establish the example of okay, a good example of that is, by the way, index insurances. I'm going to explain, but let me just tell you. For example, in index insurance, let's say in agriculture market, because agriculture market is one of the things that I study, and usually my examples are from agriculture market. You for example, have an insurance like a temperature-based insurance, right? For example, if the temperature goes down, your harvest gets damaged, and you're automatically be paid, right? Their temperature is the systematic part, right? So this is why I'm saying that the model that I'm proposing is not only useful for macro risk management, it is also useful for the type of risk that we usually deal with, right? When we have a systematic component, and in crop insurance, temperature is a systematic component, right? Okay, and then we establish a universal rule of allocation pricing, and also establish X and reinsurance. I'm going to skip this one because I have another part in the paper that I need to explain. So now let me start step by step, actually introducing the factor model. Okay, as I said, what we have in literature is like IID sequences, right? This is very usual. But one way in literature to generalize that is to use exchangeable. And you know, exchangeable means that it is very much like IID, but they are not independent, right? That means any finite number of the sample that you get, the joint distribution only depends on the number, right? So this is very much symmetric, right? So that's why they all have the same distribution, right? But they are no longer independent, right? But there is a theorem, it is very well understood in the literature of probability. There is a theorem saying that if you have an exchangeable portfolio, then it can be presented as follows. There is a function chi, a common shock z, which is a random variable shared among all, and an IID sequence yi that xi can be written as follows, right? But this is a very, very nice theorem because it gives now an idea how to depart from even the exchangeable models to introduce a more sophisticated model. Why? Because it says that an exchangeable model is nothing but a common shock, which is the systematic risk, an IID sequence, which is the idiosyncratic risk, and a link function or connection function that relates them together, right? So then I would ask why we should not go on the same path and generalize this, right? So that's why I'm going to introduce factor models as follows. I say, okay, let's keep the very same structure. For any xi, say we have a link function or connection function chi I, and we have a systematic shock zi and idiosyncratic part yi, which is specific to the individual. But still, I have to say what is the structure, what is the rule that they are following. First of all, because this is systematic risk, it means that these ZIs are highly correlated. They should be very similar to each other because they are sourced from a very similar, I would say, phenomena. For example, they are related to temperature, their temperature, or they are market risk. If you want to think of a financial market, they are market risk, right? But YIs are independent. This is just something like innovation. We call it in finance, right? So, and then these chi-Is are also a link function that link them together, right? Okay. But this means that now we have a good model, but still how to implement heterogeneity. By definition, it is already heterogeneous because it seems that they have different xi, chi i's, zi, y i's, and chi i's. But that is not good when you want to prove theorems, first, and second, it is not realistic. For that reason, I'm going to put a little bit of a structure on indexes, because each index is associated to a type of people, right? What is the mindset? My mindset is that, let's say we have different losses, right, which are introduced this way for different individuals, but it is not that all individuals are totally different. They only share in the systematic risk, right? They share the systematic risk. It is sort of that people are of different types. And then I can say, for example, this type in my whole population is more populated, type 1. Type 2 is less populated. Type 3 is extremely low populated, right? It means that I also want to put a little bit of structure on something that I want to call it typology and say, these I's cannot be arbitrarily given. They belong to a structure of distribution, right? So that is why I would say, for example, if I consider people are of different types, index are designed so that they follow some sort of distribution. I call it the typological distribution. And this is saying that how these indexes are actually distributed. How many of type 1 people we have? For example, let's say I want to understand how many of people who are at high risk we have. Okay? How many of people, or let's say, what is the percentage of high risk people we have? What is the percentage of middle risk we have, or medium risk we have? What is the percentage of low risk that people we have, right? So that is why I can give a distribution. You can think of your own example, for example. It can be related to health. For example, if you are thinking of machine learning, you can say this is a distribution on the features, right? People have different features, and you want just to put a distribution on the features. And for that reason, you can come up with a distribution of the types, right? But I want to follow 3 principles. First of all, if types, which I denote them by tau, and for individual I assume that it has actually type tau I. If you have 2 people who have very close types, their systematic shock also should be very close, because they are experiencing the same thing. For example, me and Ed and other colleagues, we belong to the academia, right? So we have very similar, we are belonging to the same sector, so it is very much that we should experience, for example, the low number of undergraduate students. This is very much happening now in the UK. All universities are suffering of a low number of undergraduate students, right? So that's why I say, because we are belonging to the same sector, to the same type, we have to experience the same common shock. And this is common all across UK, that all universities are experiencing low number of undergraduate students, okay? So this is the principle I want to have for the systematic shock. For the other one, for the idiosyncratic shock, on the other hand, I want to see if types are very close. Apparently, they are independent, because by definition, idiosyncratic means independent risk is yi's, right? You remember that? And this structure, these yi's, they're independent, right? But their distribution, which I denoted by G, that means they CDFs, cumulative distribution. If they have similar types, they should have similar CDFs, right? Because if we belong to the same, for example, sector, again, say, that means we have very similar personalities. And personality means, or family, or background, usually are very similar, right? So that's why we would experience very similar type of risk, not identical, but in terms of distribution, very similar. So that's why, for example, if you go to banks, For example, professors are very highly ranked when it comes to credit assessment, right? Because it seems that they are very similar in their idiosyncratic risk, but it means that they have independent idiosyncratic risk, right? But they have similar distributions. And I also want similarly to see when types are very close, their link functions, right? Okay, there are many examples in the literature. I just dropped the papers that use link functions. They don't call it factor models, but they do exist. You can find them. I can send you the research papers that are using that. For example, we have additive models where they call it common shock. And then we have idiosyncratic. We have multiplicative. I'm not sure if you remember Rudu's talk. He was using a multiplicative or a common shock in his talk. So it is very popular. This also is called mixture. This is called fatal. Fatal is very useful when you want to model fatality. That means you will die either of a common shock, like a common event that comes, or you will die because of a personal cause, right? So that's why we have fatal. We have two states. That means we have a state of corona or not. And we have parametric models, and we have apparently in finance this type of linear factor, right? So that's why I'm saying the idea is that how to unify all these things in one framework, right? Okay, but what is the theorem? I have to be faster. I started, I think, 9 minutes late, right? So, yeah. Okay. The main theorem is as follows. With some assumptions, the pool risk goes to this. And what is this? This is just the integral over the distribution of the types of what? Expectation of xi condition to z, right? Okay, now let me interpret this. The interpretation of this is as follows. Expectation of xi condition to zi means that you are just averaging out all the idiosyncratic risk and just keeping zi, because it is conditioned to zi is left, but yi is averaged out, right? Okay, so the message is as follows. If you pool, then what is going to happen is that all the idiosyncratic risk goes away. You are left with the systematic part. It is going to be the aggregate systematic loss, right? So that's why I'm saying when you're facing systematic risk, pooling is not of help. That's why insurance is not useful in Corona, right? In COVID, right? Because insurance is just designed to remove the idiosyncratic risk, not very much the systematic risk, right? So that's why you need to make observation. You need to move to ex-post policies rather than ex-ante policies. Ex-ante policies are only good when you're dealing with idiosyncratic. And a corollary, which is really interesting, is as follows. Let's say now you want to do risk management to measure the risk of that, right? So let's say I'm using an additive risk measure like value at risk or conditional value at risk, which are very popular. And you also assume that actually these shocks are equal to each other. That is why it is a common shock, like COVID. Everybody is the same, right? It's not like they're similar, they're the same, exactly the same. So two assumptions. First, common shock assumption, second, additive. Then you can take a row of both sides, but interestingly, row will exchange with the integral, and this goes down inside the integral, right? So, but this has then a very, very interesting interpretation, because this is the aggregation of the risk that you measure after you observe the systematic risk record, right? But this says what? This says that this theorem that if you want to manage the risk, first pool to get rid of idiosyncratic risk, and then share in order to get rid of systematic. So that means this gives you a good recipe, or a rather reasonable recipe to manage the risk when you have idiosyncratic and systematic. This was only for idiosyncratic. This also gives you for systematic data. First pool, then share, right? Because this is risk sharing to some extent, right? When you exchange the role of intake loss. Okay, and then I have a central limit theorem. I'm going to skip that one. That was law of large number central limit theorem. It is conditional central limit theorem. That means you have to make first the observation and then come up with the limit. So that's why conditionally this goes to a limit of normal 0, 1 when you normalize everything. I'm not going to discuss that a lot. But one thing that I want really to mention is about a universal rule that is really important of risk sharing. We know that Denouy and Dunn have introduced this expectation law, right? This is very famous, well studied. But the problem with this law is when n goes to infinity, or even here, right? Let's say we have all these expectations that shares how you would come up with allocation, right? But let's say if these follow my model of factor risks, for me, the idiosyncratic part is not important because that is too noisy and I'm going to pull it anyway, right? What is important for me is the systematic part, right? So that's why if I say I have a common shock model, I rather want to see this law. That means the important bit of risk when you're facing systematic risk is not the noises, the idiosyncratics. It's just the systematic. So that's why I would rather prefer this one. But it's really interesting that this is going really to happen when we send n to infinity for all type of risk sharing rule. I'm going to explain to you, not only for expectation law. So that's why expectation law of this kind is a universal. So for that reason, first I have to introduce ex post risk sharing rule. Ex post risk sharing rule is just a risk sharing rule after you make the observation, right? So you make the observation on a variable that you want. Okay, let's say I have a random variable x1 to xn. I want to do the risk sharing. I already assumed that my consideration is that you know what is risk sharing, right? Let's say I have a vector x1 to xn. I want to do risk sharing, but they are subject to common shock, right? So as I said, because we have justification to do it ex post, we have to make an observation. Here I change the role of z to v, right? So v is like z. You first make the observation. When you make the observation, then you come up with a joint distribution. That joint distribution then is subject to be of risk sharing, right? Subject to risk sharing. So that's why I say ex post means that I do risk sharing for this after I do the observation for V, right? The common shock to some extent, right? Okay, pick just any rule like the ones that Ed already have developed for many years, right? And do the risk sharing, right? There are very few assumptions, and most of the risk sharing is happening here, right? Okay, you come up with something like this. You know, this is the summation, and this is the individuals. And then let's say I want to send n to infinity, right? And then take the limit of this risk sharing and say, then associate it to random variable x. So that means x is within an infinite pool. And for finite ones, I'm going to calculate this and then send n to infinity. So that's why this is some sort of risk sharing value after risk allocation, value after you send n to infinity. But here is the theorem. The theorem says that if you use factor models, all these rules, regardless of what risk allocation rule you're using, regardless of that, almost, I mean, not in without condition, but very, very minor condition, they all converge to this expectation rule. And this, I think this is very nice because it says that this is a universal rule if you are dealing with large pools. Okay, I have to move faster. It seems that I have 5 + 9 to like 12 minutes or 14 minutes. Right?
I think you can definitely go.
Okay, so let me also explain this fact. Okay, that was the whole story about factor models. That means how to benefit the knowledge that we have from the factors in order to create better models, right? But now the question is how I can use the knowledge that I have from factors to do a better risk assessment. So that's why I introduced factor risk measures. And I have to mention that in this paper, my colleague Peng Liu, I'm not sure if you know him, he's my colleague at Essex University, has a great contribution, right? So that is why most of the theorems, I would give the credit to him. But what is the motivation again? The motivation is again the same. This is something that is happening already many times in literature, and then I realized that it's better to put them in the same framework, right? So what are the examples? Let's say, okay, the idea is that to benefit the knowledge that we have about a systematic factor in order to make a better risk assessment. Okay, let me start from regression. Regression is very simple thing. Regression is what? You have a set of W here is just a vector, right? For example, in regression, it is the vector of independent variables, right? When you want to do the regression, what you're going to do? You're going to take the expectation of something that you want to explain, right? Given that you know all those independent variables. This is essentially what we call it regression. Actually, Ed in his papers has a more general rule when he uses risk measure here, right? That is, I see that he also named them regression. And okay, but here it is like you have the role of factor, right? The common factor and the individual that you want to make the assessment. Then we have all these allocation rules. That is, okay, I cited just 3 of them here, but there must be more of Ed papers on this with his co-authors that again uses the very same idea, right? So giving an allocation based on a risk measure that has 2 arguments, and one argument can be treated as a factor, major factor, and the other one is the individual. If you're familiar, you know this is the law that you have a weight function, you insert Sn here in order to find the allocation, and these are xi's, right? But you can remove just those i's and replace Sn by W and just introduce this risk measure. Then we have systemic risk measures in the literature, which again follows the same concept, the same mindset. I'm not sure if you know Kovar of Broom-Meyer, who is an economist at Princeton University. He very much popularized this for many years. It is used for systemic risk in banking, right? Banking network. That says we have to take value at risk when we have the knowledge about the whole system risk, right? For systemic risk. And after that, people followed introducing co-expected shortfall, not using value at risk, but using expected shortfall. And then finally, many papers followed, and finally, Jan Dunn and his colleagues said, okay, let's put it in a very general setup. Let's say we want to introduce a risk measure like this here. Rho lambda and rho gamma are 2 distortion risk measure, and say we introduce a risk measure as follows, where you want to measure the risk of a distribution condition on a systemic event, right? And that systemic event again is introduced based on another risk measure. A particular case is going to be Kovar and also expected shortfall and all those things, a co-expected shortfall. But again, it is following the same rule. That means you have a systematic thing and then individual thing. And also my first explanation about the universal rule, which is also following the same thing when the Z is the major factor, right? So, and we have other examples. I see recently a paper on arXiv that is using the concept of environmental risk or risk of environment, something like that, instead of systemic. So that's why it seems that people are realizing that they should be unified in one framework. So just simply a factor risk measure is just a 2-argument risk measure when it takes the individual risk and a vector of factors and just give you a number, right? Okay, but always you have to go to axioms. when you want to introduce a risk measure. And this is a list of 12 axioms. I'm not going to explain. Most of them are known to you. Usually you fix W and then discuss about the first argument. For example, additivity, linearity. This is linearity, right? Then you have comonotone additivity. That means X, X1, X2 are comonotone. Then they open up like value at risk and conditional value at risk on actually comonotone distortion risk measures. You can have monotonicity. You can have comonotonicity. Your comonotone monotonicity. You can have normalization. That means risk of 1 is equal to 1. Okay, in almost all these axioms, we always fix W and work with X, which is not fair because you would say, what is the point when always fix? Only some axioms 7, 8, and 9 relate the two. For example, 7 is low invariance, and low invariance is not in terms of X when W is fixed, it is in terms of the whole X and W. That means you also can have a rule where it is low invariant with respect to X and W. We have risk shapeless, which is very nice. It's if you consider a risk, an increasing function, and you apply to W, this is not going to change. Actually, we introduced this because we have seen many examples on that type, like Kovar following this. So that's why it is free of the shape of the factor, right? It's only genuinely focuses on what is happening in the risk, right? You can't just take out all the shape of that. And you also have ordinality. Ordinality is very much like exchangeability in value at risk that we have. That means if you apply an increasing function to the first one, it can just come out, right? We have it for value at risk, right? But here we need to introduce it for a general case. Actually, we have already characterized risk measure with these properties. They are very much like value at risk. Okay, so now I move faster. This is the first theorem. Some sort of Shochet integral we can introduce if we consider comonotone additivity and comonotone monotonicity. This theorem is actually a very, very important theorem. We realize later because this is an extension of a very famous theorem in the literature of economics, which is already published many years, and people know that in JET, economic theory, but we use a lot less assumptions, right? So that is why if you have only these two assumptions, comonotone additivity and comonotone monotonicity, then you can represent your factor risk measures as follow, where here CW is sort of very much like a capacity. But this is the theorem that I want to present because it has a lot of application. If you have comonotone additivity, you have monotonicity normalization, increasing, it is some sort of continuity, maybe you cannot remember. These are very familiar, and low invariance, that is the important bit. Then this can be represented very much like a distortion risk measure. And this is if and only if. Very much here, if we don't have these things, this is exactly distortion. That means what? That means there is a function phi, which is a function of two arguments. One of them is the factor, and one of them is u, that you can write it this way. But there is a problem here because you would ask, what is this u? This u is just a uniform zero-bond random variable, which is comonotone with x. And now this is becoming funny because you say, okay, you wanted to get rid of x and put everything with regards to x in value at risk, while it is still here. So that is why this is not a good representation. This is, even though the theorem is very difficult to prove, but you would say this is not a good representation. But if you are familiar with the literature on risk sharing, you understand that this is very useful for risk sharing. Why? I'm not sure if you know. We have an assumption in risk sharing, we call it no moral hazard assumption. That means when you want to do the risk sharing, the variables should be comonotone in order to remove moral hazard. And that means that all of them are comonotone with one unique uniform zero-bond random variable. Not very much unique, but up to something, right? So that's why if you have n random variables x1 to xn that you want to do the risk share, actually to come up with the design of a risk sharing or reinsurance, first of all, you have to assume all of them are comonotone. That is why all of them have the same U. And when you have all of them have the same U, it is as if U doesn't have any role, right? So that's why this is very useful actually when you want to do risk sharing. Okay, I speed up. How much?
I would say you have to wrap up.
Okay. Just we have examples of these things. Okay, we characterize COVAR, which is very nice. COVAR can be represented in our framework. Its famous risk allocation rule is within our framework. According to that representation, we needed just 5. This is the 5 of those risk allocations. The Young-Dunn's rule, again, we can represent it the same way, just we needed the 5, and here is the 5, and so on, right? So I'm going to skip all those things. I was just saying that this has an application in risk sharing, and they are quite different than the ones that we use it for with just one unique risk measure, I mean, without factors. And it shows that here, I'm not saying what are these, but just wanted to show you the difference between using a distortion risk measure and a factor distortion risk measure in risk sharing. This is something that says how much risk allocation you want to do. You don't understand it, perhaps just want to show you that how much gap a factor may actually inject in the rule that you want to do for risk sharing, and if they really matter, if you want really to use them, you have to. Otherwise, you will come up with very, very bad rules if you want just to ignore that. And that is obvious because managing risk without considering factors, it is as if you're underusing your information. Okay, just conclusion. Okay, the idea was like how we can benefit the idea of systematic shocks or factors or whatever you want to name it in introducing good models and in finding good way of risk assessment, right? So we have done it through introducing risk factor models and risk factor risk measures. So factor models and factor risk measures. And we show that you can come up with very nice rule. For example, for the first one, that was only one theorem I presented. You always come up with a universal rule of risk allocation. And for the second one, definitely within our example, you see that risk sharing totally have a different profile when you want to benefit the factors information in your model. And I think there is a long way to explore these things in the future. Okay, thank you very much.
We have just a bit of time for questions, either from here or from, well, because I'm blind, I don't see anything. Someone will have to help me with the Zoom.
In chat.
The chat.
Yeah, this is just a message.
The remote attendees, if you have questions, please do not be shy and just ask. Why the participant?
Hi, Hirbod. Hi.
Hi, how are you?
That was a great talk. Thank you, everyone. This was my first time attending center, so I appreciate the open invite. My question is regarding the usage in the field of finance. Like for a long period, we have been discussing systematic and systemic risk and the idiosyncratic risk removal. But I think the beauty of your work is that it's linking them in a, I would say, comprehensive way with the financial models. So can you tell me more about the practical usage in the field of finance?
Yes, I can give you one example. I'm not sure if I'm very much right on that, but anyhow, that just come to my mind. I remember many years ago when I was doing PhD in economics, I was working, actually, those papers in my economics thesis still need to be published. So, but I was working on pricing rules, right? And you know what is a pricing, or sorry, a stochastic discount factor. And a stochastic discount factor is nothing but a random variable where you can apply to your risk variables and take expectation. It is like a radon-Nikodym derivative of the risk neutral probability, right? When you take the radon-Nikodym of risk neutral probability, you come up with a stochastic discount factor, right? In economics, they have a different view. Economics and finance, they have different view. They just call it the stochastic discount factor and try to estimate it, right? And the way that they estimate it, they use factors, right? So they have linear models for that. For example, the major factors that they can use is usually sum of range factors, for example, 3-factor models. Or even in my thesis, I use 7 different factors. For example, I use also a momentum factor. I also use a factor for corporate bonds or whatever, right? So let's say you have a number of factors, but what is in the literature is like, usually they use a linear models, right? But interestingly, my supervisor was doing great research on that with other colleagues of him. And one of them I met afterwards, after I finished my PhD, and he was saying that over the years that we were doing this type of stochastic discount factor exploration, that how we should look like, and we always use linear models. Now I come to conclusion that linear models don't work, right? So we need to depart from the assumption and go to non-linear models, right? Because the result convinced him that these are not very well pricing the assets in the market, right? So my framework is very much opening the door to that extension, right? So saying that if you want really to look at the factor models, you can do it very properly, right? You can do it in a very non-linear fashion, right? And there are good candidates for them, the things that have been already used in the literature, and you can consider them, right? So that's why I'm saying perhaps it is useful when you want to use it for finding a stochastic discount factor in a non-linear fashion. I know there are other works on that. I'm not saying that this is the only one. Even people are using, for example, like machine learning techniques nowadays. I've heard about that, but still, this is opening the door towards that. That can be one application.
Not sure. More questions from the remote?
Yeah, thank you.
Yeah. I just also see my co-author Peng Liu. Actually, I have to thank him because many of the theorems in the second part of the paper is due to him and his effort. Anyone here?
No, I guess. We should be wrapping up. Thank you very much.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thanks everyone on Zoom.
Thank you. You have to stop sharing.
Okay. Have a good day.
Bye.
Bye.
Bye.